Hi, Assalamualaikum. We are still in chapter 4, early chapter 4, which is the frequency response analysis and design technique. So in the previous video, we have learned about the concept of frequency response, where we have learned about magnitude frequency response and the phase frequency response. So these two responses, the magnitude frequency response and phase frequency response, can be plotted for us to analyze and study the system. So this is about Bode plot, and we are going to focus on the basic factors of transfer function. In control system engineering, there are several methods introduced to plot the magnitude frequency response and phase frequency response as the frequency varies. The famous and usually used methods are the Bode plot, the Nyquist criterion plot, and the Nichols chart. However, in our syllabus, we are going to cover only the Bode plot. A Bode plot is a graph of the frequency response of a system. It is usually a combination of a Bode magnitude plot expressing the magnitude of the frequency response and is measured in dB or decibels, and also a Bode phase plot which expresses the phase shift and measured in angle degree. So this is the frequency response that we are studying, which consists of the magnitude and the phase shift. And the magnitude and phase shift is plotted in the Bode plot like this. And usually we plot both the magnitude and phase shift in the same sheet or same semi-log graph paper. So this is the semi-log graph paper looks like. I guess everybody have seen this before and have applied it on your previous study, but let us review the semi-log graph. Okay, so it consists of the y and x-axis. Okay, we can see that the y-axis is a linear scale. It is evenly divided and even with even spaces between numbers. Okay, and this is going to be our magnitude scale, and the unit should be in dB. Okay, so the horizontal axis or the x-axis is going to be our frequency, which is measured in radian per second, and we can see that it is logarithmic scaled, which is equal scale between power of 10. Okay, so usually we are going to use the same semi-log graph to plot our magnitude and the phase angle degree. Okay, so this side we are going to scale our magnitude in dB, and this side we are going to scale our phase angle or phase shift in degree. Okay, so in this same sheet we are going to see two graphs being plotted, which is the magnitude and the phase angle. The log magnitude and phase frequency response curves as functions of log omega are called Bode plots or Bode diagram. Sketching Bode diagram can be simplified because they can be approximated as a sequence of straight lines. So this is an example of a phase shift plot for a frequency response. So at the y-axis, we can scale the phase angle in degrees, starting from 0 to 90 degrees, and the horizontal or x-axis over here is being scaled in frequency or radian per second. We can see that the scaling is in a power of 10, okay, starting with 0.01, 0.1, and it increases for a power of 10, 1, 10, 100. Okay, this period over here is, we can also call it in as a decade, 1 decade, and this is also 1 decade. Okay, so the range from 1 to 10 is called 1 decade. Okay, so actually we start our drawing with an asymptotic approximation straight line. Okay, so it simplifies our evaluation of magnitude and phase frequency response, and we can also at the end draw the actual curve of our frequency response. The frequency response of a system is actually the transfer function where the S domain is transformed into the J omega domain. So let us consider the following transfer function. So this is the general form of a transfer function, which consists of the k and factors of zeros, and the denominator consists of the s power of m and the factors of poles. And this is the magnitude frequency response, which is actually transformed from the S domain into the J omega domain. So if we know the magnitude response of each pole and zero term, we can find the total magnitude response. The process can be simplified by working with the logarithmic of the magnitude, since the zero term magnitude response would be added. Okay, these are the zero term magnitude response being added, and the poles terms magnitude response being subtracted. Okay, we can see these zero terms being added and the pole terms being subtracted. So from the magnitude frequency response, we can obtain the basic factors of J omega. So we have K as our gain, derivative J omega. If we have an S at the numerator, so it is considered as our derivative J omega, and integral 1 over J omega. So this is going to be our integral part of our frequency response. And we have first order factor. These are our first order factor, and a second order factor. If we have s power of 2 plus constant s plus another constant, so that is going to be our second order factor. So assuming that our frequency response can be consists of these all factors: the gain, derivative, integral, first order factor, and second order factor. Let us look at an example 1. From the given transfer function gs, obtain the basic factor of gj omega. So this is our transfer function in S domain, which consists of the numerator of 60,000 k and the first order factor s plus 60. And in a denominator, we have an s and s plus 100 and s squared plus 10s plus 36. So what we do first is we are going to transform the s domain into our j omega domain. So we get gj omega. Just change all the s into j omega. So this is the 60,000k, and we change the s over here with j omega, so we get j omega plus 60. So this is the first order pole, and change s to j omega over here. S plus 100 becoming j omega plus 100, and s squared becoming j omega squared plus 10 j omega plus 36. So from this frequency response, we can identify which is our gain, which is our first order factor 0, which is our integral. We don't have a derivative over here. If we have an s at the numerator, so it is going to be our derivative, but we don't have that in this example. So we only have an integral, which is equals to 1 over j omega. So this is our integral part. This is our first order factor pole, and this is our second order factor pole. So next, we are going to simplify our frequency response. Okay, how to simplify? We just look at the factors, first order factors and the second order factors. So what we do is we have to divide our first order factor here with 60, so that we can get this kind of form. So if we divide this with 60, so we have to pull out 60 to be multiplied with the factors. Okay, so the same process goes to the denominator factors. So this first order factor divided with 100, so we pull 100 out, and this second order factor we divide with 36. Okay, so we pull 36 out, so we simplify everything. Finally we get the frequency response in this